This begins the 555 with Dr. Zahid. It's April 8th, 2014.
Thank you, sir. Thank you very much. Good morning, everybody. Let's continue our discussion from last time. Can you zoom in, please, a little bit? Thank you very much. Okay, we started looking at an overview about the next generation IP, which is referred to as the IP version 6. And again, as I told you, this is not a new protocol. It has been in development for more than 20 years right now, but it's still struggling to get a wide deployment across the internet. The motivation for IP version 6, again, as I told you last time, is that they were running out of IP version 4 addresses. Out of IP version 4 addresses, they wanted to increase that address space. At the same time, they said that as long as we are going to be looking at the address, we might as well look at the entire functionality of the IP to see if we can improve some things on the header, for example, to speed things up, as I will show you in just a second, for quality of services, to provide for multicasting, to provide for mobility, and so on and so forth. Now, in the meantime, this one is trying to provide all of these things. In the meantime, these things were separately about it throughout the semester, separately provided in conjunction with the IP version 4. They change, as I will show you in just a second, is that the header, instead of variable length, fixed length header, as I will show you in just a second. Okay. Again, as I told you this time, the explosion in the internet-ready gadgets or devices require in the address space. Let's look briefly at the headers of the two version 4 versus IP version 6 to see what has happened from one header into another header. Let's compare it side by side that you can see. Of course, is the version of the IP. Which version of the IP is? It's IP version 4 or IP version 6. Now, we do have what? The header length. The reason that we need to have a header length in here is that because it was variable. It was anywhere between 20 bytes to 40 bytes. To 60 bytes. As in the IP version 6 header, they decided on a constant header, on a fixed size header, 40 bytes. So in the case of the IP version 6, they have 40 bytes header fixed. So that field is not included in here. Clear? Okay. The type of service, again, at the beginning of the semester, the type of service was used in IP version 4 to provide services. Different services to different types of packets depending on the need. They change IP version 6 into what? Into two separate classes. The traffic class, which is basically the same as the type of service class. Which class is it? Class 1, class 2, different classes require different types of services. Added another field, which is an interesting one, which is referred to as what? A flow label. A flow label in a group of packets belonging to the same flow, a group of packets belonging to the same flow to be weighed by the network. They refer to it as a what? As a flow label. The entire second row of the IP version 4 header, which was for fragmentation, it completely. And IP version, if you remember from 450, was done. Why do we do fragmentation? Let's see if you still remember. Why do we need the fragmentation? Because the packet does not fit into what is referred to as the MTU. MTU stands for Maximum Transmission Unit. In IP version 4, both the source and the router to fragment the packets. In IP version 6, only the source can fragment the packet, fragment packets. They wanted to speed things up across the internet. So fragmentation is not allowed. It's only done by the source, clear a source. So the entire row was removed. Now, next we have what is known as length. In here we have only a payload length. Why do we need only a payload length? Payload length because the header is fixed. In here we do have a header length and a total length. Subtract the header length from the total length, you get the length of the payload. In here, length. We don't need the total length because the header is fixed. Okay. A protocol represents what? What type of protocol is being encapsulated inside the packet. In here, they a different procedure, similar results but different, which is what is referred to as a next header. I'll explain this one to you in just a second. Let's leave it for a minute. In a minute. Time to live, they call it a hop limit, which is basic. If you remember the time to live, every time a packet goes through a router, the router will decrement that. It reaches 0, it will drop the packet. In here, they opted of what is known as a hop limit. Again, number of hops. Every time a packet goes through a router, the router will decrement this counter. 0, it will be dropped. Of course, in here we do have the source address and the destination. Each one of them is 32-bit long. In here, the source address is 120 long. So it is 4 times as big as this one, 148-bit long. And here also 128-bit long. 128-bit long. For a total from here to here, the header length, the payload, by the way, this one, which means the payload length, the payload, max is equal to this 16 byte length is equal to 40 byte. Now, the difference also, another difference, which is the last difference between the two, is the following. There were an option field. An option field in the packet IP version 4, in the option field, it's up to 40 bytes. This one here. See, for 20 bytes, and there is an option field, 40 bytes. What did they do here? They did here a very interesting thing here. They said that most of these options are not actually processed by routers. They are processed by what? By the end systems, by the source and the... Why do we need to include them in the header? Why do we need to include them in the header if the routers and the internet will not process those options? Will not process those options. So what they did, they decided to take this option field and they put it as part of the payload. Here is what? This is the payload. They want options. If they want options, then the next header, this next header, will point to here. It will point to here. The next header will point to here. These are what? Several extensions. Look at it so that you can see what I'm talking about. Okay, here, payload, it may include several extension headers. But it's part of the payload. It's part of the payload. So the routers will not look into this one here. Only the end systems will look at this one here. It's not, this one is now the base header. These are what? Extension headers. And there is a field in here that is called the next header that will be pointing toward what? Toward the next payload inside the payload. So for example, let's assume there is no extension header. There is no extension header. So what, in other words, which means what? It means in here, whatever the protocol that is being encapsulated inside this. So for example, if it is what? If the next header is TCP, being this, this next header. If it is TCP, then what we have is the what? Is the IP, which is this one. And then the next header is what? TCP. And what do you see in the payload? In the payload, you header plus the what? Plus the date. So in this case here, there is no what? In here, no header. No extension. Let's look at what this one is all about. IP version header. This IP version 6 header, which is this header here, pointing to another header. The next header is what? Is a source routing. Source routing header. Source routing allows the source to decide on what? Which route. Allow the source to decide on which route. In the payload, the first extension header will be what? The routing. Then what? The next header means what? Next header in here. The next header has what? Next header and what? The length. The next header is what? So, and then you see what? TCP header plus what? Date. So in here we have one extension header. One extension being the routing. Let's look at this. We have two extension headers. What is IP version 6 header? This is this one. The pointer is pointing toward what? Pointing toward the next header, which is the routing. Routing header is pointing toward another header, which is what? Fragmentation header. Fragmentation. Then what? The fragmentation header. The next header is TCP. Then you do have fragmentation, fragments of TCP header plus the what? Plus the date. So in this case here, we do have what? Two plus the what? Plus the payload. But all of them are part of what? All of them are part of the payload of the IP version 6. Routers are not interested in any one of these. They're not interested in any one of these. So they will only be processing what? The base header. Whereas was in here, the routers were what? Were going to process all of these options because they were part of the header. Now all of these extension headers are part of the what? So they are only being what? They are only being processed at the end systems. So that's one of the major differences between what? Between IP version 4 and IP. One last thing that they removed, which is what? Which is the header checksum. The header checksum was also from the header. In the IP version 4, every router across the internet was going for errors. In this case here, they said what? Let's remove this checking altogether. We don't need that. There is error checking. In the fourth layer, there is error checking. Enough of this error checking. Clear? Enough of. So they removed it totally from the header. There is no header checksum at the header of the IP version 6. Clear? Okay. So anyway, when I hold you responsible for this, I don't want you to memorize these. I just want you to understand the differences. And on this will be in the true and false section. Did you get my point? In the true and false section. So what changes were made in the header from here to here. But I don't want you to memorize all of these things. Okay. So one more time, the important thing that has changed is the removal of the options fields on extension header so that it speeds up or it becomes what? It on the routers inside the internet. Clear? Okay. The next question that they needed to answer is the following. Is that how are they going to deploy this IP version 6? All the routers in the internet is what? It have IP version 4. A person suggested, and everybody laughed at him. One person suggested is that they call it what? He proposed that they call it a flag day. It's like Independence Day or Thanksgiving Day. He suggested that they call it a flag day, where everybody stops working. So you don't use computers, you don't use gadgets, you don't use your smart whatever device that you use. Don't use it for a day. Allow what? Allow all the network administrators, where we have millions of them, to install IP version 6 in the what? In the internet. And they told him, I just declared that you cannot designate one day, everything stops down, and the what? Update IP version. So they wanted some transitional period. Transitional period means what? A period in which IP version 4 and IP version 6 can coexist together. Excuse me. Can coexist together. So one possibility, one use is They use what is known as what? Dual stack. They use a dual stack. Give me a moment. Sorry. They use what? Dual stack. Dual stack means what? Means you implement both IP version 6 in your computer. So it has what? It has two stacks, which means how many addresses? You would need 2 addresses, IP version 4 address and IP version 6. So my question to you is the following. Let's see if you can tell. If I want to send a packet to which address will I use? I use an IP version 4 address or I use an IP version 6 address? Do I know whether the receiver or whether the destination is using or has IP version 4 and IP version 6? How do I know that? And which one do I use? Well, they said, how would you address of a destination host? How would you get the IP address of a destination host? How would you get an IP address of a destination host? Nothing. How do you get the, forget about IP version 6. How would you get the IP address of a destination host? I want the IP address of a destination host. How do I get it? I get it through the use of DNS, service, clear a domain name system. Now, in a domain name system, you are going to supply a host name. Host name, the server will return to you a what? And in this case here, whatever the server returns to you is the one that you will be using. So if the server returns 4, you are going to use IP version 4. If the server returns IP version 6, you are going IP version 6 in your response. Clear? So it depends on whatever the server returns to you. Now, in this case here, for example, IP version 4, you will talk with what? You will talk with all the systems in here that employs only IP version 4. We'll be talking with what? With IP version 6 systems. So in a dual stack, IP version 6 to a system, do not delete IP version 4. Do not delete it. Clear? Do not delete it. It's a unique habit in addition. Okay. This approach, by the way, is used similarly with other types of calls that are proprietary protocols. For example, AppleTalk, for example, NetWare, IPX, all of the what are proprietary protocols. You will see it implemented as what? As dual stack. If you look at your system, for example, you will see it has its native networking protocol stack and it has a what? A TCP stack. It has both. Clear? Okay. Now, in most cases, again, IP bundled within your operating system releases. In you operate, for example, Windows 8 and so on. These new versions of operating systems, IP version 6 is already what? It's already bundled. You need to what? You don't need to install it separately. It installs directly with the operating system. Not an extra cost add-on. With the operating system. The applications will choose to use when initiating base response. If the DNS response is IP version 6, so you use IP version 6. And so IP version 4, you use IP version 4. This allows the indefinite coexistence. Indefinite will be what? Could remain forever. Could remain forever. But on what expense? On the expense of the dual stack in your what? In your computers. And everybody needs to what? Once you deploy, to upgrade your operating systems, this one will automatically what? Will automatically be apart. You need to update the DNS all of these DNS servers to have what? To have two sets of addresses, IP version 4 and 6 addresses. The other solution, which we are already familiar with, to as what? Tunneling. We saw tunneling. Where did we see tunneling? We saw tunneling in the case of what? Mobile IP. We also saw tunneling in multicasting. And multi-routers do not support multicast routing. You could use what? Tunneling. In here also we tunneling. Let's see the scenario in here. We have an IP version 6 here, an IP version 6 in here, but we have what? IP version 4. In between we have IP version 4. These routers do not IP version 6, do not support IP version 6. So what do you see? You see that a tunnel will be created. This is created between router B and router E. In reality, and within this tunnel, there might be what? Multiple routers inside. But E, it looks like a what? It looks like a point-to-point. It looks like a point-to-point because you are going to establish between B and E. So now, let's see what happens. Let's see what happens. B, this is the original packet. The packet is which version? Is version 6. B, packet of version 6, and put it in a payload. Put it in a payload of version what? It add what? It added the header of version 4. And the header of version 4, what does it have? The source IP address. The destination IP address is what? E. So you have created a what? You have created none of these routers inside the network or inside the tunnel. None of them will see the payload of the packet. They will only see the what? The header. And the header being what? The header being of IP version 4. So the packet get what? Routed across the what? Across the network, port IP version 4 until it reaches to this point here. And then what does E do? E will remove the header, remove the outer header, which is the IP version 4 header. And what remains is the what? Is the IP version. And it will what? It will forward it to E. Remember, it will forward it to F. Remember, these can support IP version 6, but this one cannot support. Now, the next situation that did you understand tunneling? Okay, the next situation is an IP version 6 wants to what? Send a packet. See, in here, where was the ultimate source? The ultimate connected to this router would support IP version 6. The ultimate destination was connected to a what? A router which supports IP version 6. This one is support IP version 6, but this one support IP version 4 only. The tunnel will not work. Did you follow me or not? This tunnel will not work if it support IP version 6. You establish a tunnel in here, then what happens? If this one does not support IP version, then the tunnel cannot be created. Clear? The tunnel can be created only if destination both supports the same protocol, which is in this case is what? Is IP version 6. Thing that they did is what? Or that they are proposing is that you transition from IP version 4 version 6 or vice versa through what is known as what? Header translation. You translate the format to another format. You don't have a dual stack, but you translate headers. Now, but when you translate header, for example, what do I have? In this region, it's IP version 6 region. Well, this is the packet, this router. Remember, none of these packets support what? IP version, sorry, router supports what? IP version 6. This router supports both IP version 4. Can we establish a tunnel in here? What is the tunnel? A tunnel will not, you follow me or not? Why? Because this one does not support IP version 6. So what does this router do? He's to translate. Notice, by the way, the payload, but the header changed from what? IP version 6 to what? IP version 4 header. Clear? Now, so all the changes that happened in IP version 6 header will be gone. Translate from one header to another header. Everything is what? All the things that IP version 6 is not going to be there when you translate the header from one format to another format. Not a very popular solution, but they needed it to what? To enable an IP version 6 communicate with a what? With an IP version 4 host. Clear? Which is what? Which is through the header translation. So the header translation, again, IP version 6 to IP version 4 for new kinds of internet devices like cell phones or cars or appliances and so on and so forth. But the benefits of this is that you don't need a what? You don't need a dual stack. Clear? Dual stack. I want you to think about this one, the header translation, the same way as you thought about the NAT, which is what? Network Address Translator. If you remember this from 450, what does the NAT do? The NAT translates the header from the private network to a what? To the public network. Clear? Work to a public network. I want you to think about this as a what? As an extension to the NAT. As clear? Clear? Oh, good. Now, the next thing that I want to show you is the addressing. The next thing that I want to show you is the addressing. Let's understand in a pad first of all. What was the, for addressing? We have what is known as what? The net ID and host ID. Clear? That's in IP version 4. That's an IP version 4. This is E450. Now addressing in IP version 6. This is the site address. I want you to think about the site address as a what? As a network address, the organization address, the IS sample. This is the site address. They are recommending 48 bits long. And then 16. This is the subnet address within the site, and the remaining 64 bits. And instead of calling it the host ID, they call it the interface ID. The interface. Oh, this is equivalent to the host. Okay, I want you to think about it this way. This is a site. This is the site. Could have what? We could have multiple subnets in here. So the address of the site is this one. The address of the subnet is this one, and of the interface is this one. Clear? Clear? This is the site organization, either a what? A private network or a what? ISP. And there are several subnets in there. This subnet, for example, subnet 1, subnet 2, and so on and so forth. And A, B, C, and so on. So. Okay, routers, forward, packets, based on what? Site address to site routers. Sorry, south routers, site routers, or access, if you would like, access routers. Forward, packets, subnets within subnet routers, within the site, and subnet routers. Packets to hosts on that. This is what is known as what? IP version 4 and 6 employs what is known as what? Hierarchical employs hierarchical routing. Hierarchical routing, which we talked about earlier in the semester, what tells you that the packets are going to be forwarded based on what? Based on the hierarchy. Routers inside the internet know about what? The subnet address do not interpret the what? Interface address. They will forward on the what? Based on the site address, forward it to the what? To the site, to the ISP, or to the address of what? I want you to think about this ISP. Listen to this. Think about ISP, and these are what? Customers of the ISP. What this one is telling you, what? Forward the packet to the what? To the ISP network. The ISP network, the routers, the ISP routers will forward it to the individual customers, and then the customer routers will deliver it to the what? To the actual destination. Clear? Actual destination. Now, a total of what again? A total 128 bits long. Again, as I told you last, if you see the total, this will be the total. This will be the total. The total number of what? Total number of IP addresses. Total number of, this is equal to what? 2 to the what? Is this a small number? Just to give you an idea. Listen to me. Just to give you an idea. The population of the whole world. The population of the whole world. Let's assume that it's one. Let's assume that it's what? 20, just an example, 20 billion. Currently. Let's assume that it's what? 20 billion. Clear? The population of the entire world. 20 billion is 2 to the what? 2 to the 30. Did you get my point or not? It's roughly 2 to the 10 is what? 1,000. So 1,000, sorry, times what? I'm sorry. 2 to the 34. Let's assume 16 billion. Simple. 16 billion. So it's what? 2 to the 34. 2 to the 30, 2 to the 34. 2 to the 10 is what? 1,000. So 2 to the 30 is what? A billion. 2 to the 4 is, so we have what? 16 billion. Let's assume it's 16 billion. How many addresses with each one of these person could have? How many? I'm not sure if you are following me. Are you following me or not? This is number of people here. Number of people. Have how many? How many addresses? Each one of them could have how many addresses? For each device they have, like for example a smartphone, they need a what? An IP address. How many IP addresses? Is 2 to the what? 128 minus what? 2 to the what? 2 to the 94 IP addresses. Did you get my point or not? In other words, each one of them will have roughly what? Will have roughly 50 billion. Are you following me? Double this one, more than double this one. Each person could have what? 50 billion addresses. So this is a huge, in other words, no way that they are going to what? To run out of these IP addresses. No way in the world. Are you following me? Okay. The reason that they opted for this big, at the beginning they decided, but then they said 64 bits instead of 32 bits. But then they said what? As long as we are, upgrading the number or increasing the number of it, go all the way to what? To 128. Clear? Now, how do we represent this? This for human use. In IP version 4, what did we use? In IP version 4, into what? The 32 bits, into 4 chunks. Into 4 chunks, each one with how many bits long? It's long, and we represented each one of them as a what? As a decimal digit. We ended up with something like 128.125.3.11. Just an which was a pretty nice way, pretty nice way to represent a what? IP address. Clear? Okay, then they said, how are we going to represent this one? Okay, now indication is divided into 8 sections, each with 4 hexadecimal digits. What is 4 hexadecimal? A hexadecimal hexadecimal digit is how many bits? No idea what hexadecimal means? Oh, this is...
The time is
This
14
is really
o'clock.
amazing. Hexadecimal digit, hexadecimal digit is what? 4 bits long. It's what? And then what? A, B, C, D, E, F. That's what? 4 bits long. And if we decimal digit, what does it mean? Each section, that implies each section is how many bits long? 16 bits long. How many sections do we have? 8 sections. Sections are separated by a semicolon. So you see it like this. Example. For example, A, B, C, 5, 0, 0, 1, 0, C, A, 3. Following me on now. Each one of them is how many bits long? Each one is bits long. 4 bits long. So in here, how many bits do we have total? 16. So here is 16 bits. This is what is referred to as a what? As a section. Again, 16 bits. As a section. How many sections do we have? How many sections? 8 sections. This one is, oh no. This is 8 sections. Now, this is also pretty what? Awkward. Do you follow me or not? And just the act. So even the, would you memorize this? If I tell you, let's see. If I tell you, would you memorize this? The answer is what? Possibly. I remember this. 128.125.3.11, which is what? The address of my, for example. But are you going to remember this? It's very difficult to remember. Okay. Leading the address notation can be simplified. For example, the leading zeros section can be the leading zeros in a section can be eliminated or represented by 1 zeros, just 1 0, as I was showing just a second. The leading, by the way, the leading means what? The most significant. Clear? Oh, by the way, most of the entries in here currently zeros. Are you following? Most of them are zeros. You can what? You can the leading zeros, every one of them except just 1. Okay, and if you contiguous sections with all zeros, contiguous. So all zeros, you can what? Replace the zeros by an extra semicolon. Let's see if you understood what this means. For example, what is this? How many addresses do we have here? Section. This is one section. This is another. This is a third. It's a fourth. This is a fifth. This is a sixth. This is a seventh. This is the one. Did you get this or not? Okay, I want you to see the second section. The second section. How come it? It's because it was what? 0, 0, 0, 0. How many zeros? How many in this section? How many zeros there are? 16 of them. Why 16? Because they are in binary. Everything is binary. You lost me? Every section consists of how many hexadecimal digits? 4 hex, and each digit, how many bits? 4 bits. For a total of how many? 6. See 0 in here. What does it mean? What does it mean? It means in this section, how many zeros? 16 zeros. I'm going to represent them by just what? 1 0. I'm just going to represent them by 1 0. Again, here the same thing. Clear? Explain to me here. What is this? FF. This one was what? 0. 0 FF. Did you? This one was 0 0 FF. What was this? 0 800. Zeros, I can what? I can eliminate them. Leading zeros. I can eliminate them. What is this? Can you tell me what? First of all, what does that mean? When I see 0, what does it mean? It means actually this one was 0 0 0. Yes? How many? How many zeros? Which is what? 16 zeros. Yes? Now, are these sections contiguous? These sections are contiguous. Then by what? By an extra semicolon. So what does this mean? This notation is this notation. So the first section, what is this section was what? FF01, yes? And then the next six sections are all what? Are all zeros. And what is the last section? The last section was what? 0 0 43. 0 0. Remember, if there is 0 0 here, I cannot what? I cannot eliminate them. Only the leading zeros can be what? Can be eliminated. Clear? Okay. So it's what? It becomes 43. So instead of what? Instead of writing the address like this, you can write it like this. Clear? Clear? Now, sometimes you see 6 written this way. Look at it this way. This is what is known as what? IP version 4 mapped. You see it written this way. 0, 0, 0, 0, 0. F means what? All ones. How many? How many? 16 ones. And then what do you see? You see a 4 address. This is, you are mapping a what? An IP version 4 address to an IP version 6 address. In the case of what? In the case of the transitions techniques that we, which is what? Translating from one header to a what? To another header. So with this, you can group all of these together and you add a semicolon here. I think this one is called a colon. Is it called a colon or a semicolon? Colon. So why did I write I think it's called a colon. They're separated by what? Colons. Remove this. Colon. All of these were what? All of these contiguous zeros was represented by this, and then what? FFF, the what? And then the IP address here. Clear the representation? Okay, good. Now, the type, before I get to this, we'll get to page 14 in just a second. Type addresses that IP version 6 support. Look at, there is a change in here. How many addresses, how many IP version 4 supports? How many types of addresses IP versions? It supports unicast, which is what? 1-to-1. It supports what? Broadcast, which is what? And it supports what? Multicast, which is what? Which is one-to-many or many. That we talked about it last week. Clear? IP version 6 decided on a different type, if you can follow the addresses. First of all, of course, is the what? Is the unicast. Unicast means address for what? On a single interface. In other words, the packet will be delivered to a single host. Clear? They call it a unicast. Multicast. In a multicast, we have what? We deliver to what? A set of interfaces. When we say a set of interfaces, it's the same as saying what? Hosts. A set of hosts interested in receiving the what? Receiving that multicast. Delivery to all interfaces in the set. Clear? Clear so far? case of IP version 6, they eliminated the broadcast. They said the broadcast is a special, a multicast. A broadcast is of a what? A multicast in which the set consists of all what? Of all interfaces. The set consists. So they change it to a new one, or they introduce a new addressing, the anycast. Let's understand what anycast means. In anycast, we have a group of hosts that have the same address. They have the same address, and the packet delivered to only one of them. To only one of them. Which one is reachable? The one that is closest, for example. Clear? Did you get what anycast means? I'm not sure. And listen to one more time. Suppose I have multiple servers. All of them identical. The contents of the server are what? Identical. They put a content provider, multiple servers, and the servers, he distributes them all over the place. They all will have the address. They all will have the same IP address. So if a host wants either any one of these servers, he will use a what? An anycast IP address, and the packet will be delivered only to what? To one of them. Which one? The one that happens to be what? Closer to the what? To the client. Happens to be closer to the client. Did you understand the anycast? I'm not sure. Huh? Say that again. No, the host doesn't know where the closest server is. No, this statement. The host does not choose which server is closer to him. He doesn't know which one is closer to him. Who? The routers will choose. No, I'm not sure you got it. One more time. You have 10 servers. They all have the same IP address. They all have the same IP address. Identical. The content of the servers are what? Are the same. A host will send a packet. Yes? With what address? What is the destination address? He used a what? An anycast address. The routers receives it. When the routers in the internet receive this packet, they will deliver it to the what? Any server that happens to be what? Closest to this router. Closest to this was reachable by this router. Not to all of them, only one of them. Once you deliver a packet to servers, then end of story. Clear? So this is different than what? Multicast. In multicast, you to deliver it to all members of the multicast. Whereas this one just deliver it to what? To one of them. Yes, that's fine. Clear? Not the host. You said the host will choose. No, the hosts are located. The host doesn't know where they are located. The host just send it to the router, and then the router what? Will forward the packets to the nearest server, which has the what? Which shares. Clear? Interesting. Also, it allows, again, it allows for the reduction in the what? In the delay, in the end-to-end delay. You don't need to to go to what? To a server which happens to be what? Far away from clients. Duplicate. You can duplicate the contents of multiple servers, especially, for example, in use servers. For example, if you look at, let's assume that we look at the server CNN, for example, which is a new. They do have multiple servers, identical information, but they are located what? All over the place. They have what? Different IP addresses. With the anycast, they can share the same what? The IP address, because they have what? They have identical material, identical content. They just happens to be what? Located all over the place. The packet will be delivered to the one that is closest to it. Now, let's get back to page 14. The addressing, the one that is most widely used, is what is known global, the global unicast address, the global unicast address. Link local, and they do have what is known as a what? Site local, which I'll show you the difference between them in just a second. All the global unicast addressing, the global unicast addressing. I think I missed one. Yes, I think I missed one diagram. Unicast addressing always start with what? With a 2. When I say always start with a 2, when I say always start with a 2, what is the first hexadecimal? When I say always starts with a what? A 2. What does it mean? What is? Clear? Clear? Is this a 2? In hexadecimal, is this a 2? The hexadecimal, a 2, is represented by what? 0010. So in a global unicast addressing is the same as what? Is the same as in IP version 4 when you say what? My IP address is such a unicast IP address. In here they call it the global unicast address. It starts always with 0010, which means what? The first 3 bits in here. The first 3 bits in here is 001. 001. The first 3 bits in here. Clear? It's a what? It's a global routing prefix. Global routing prefix. Help me here. Where is it? Where is the global unicast? It starts with what? With what? 001. How do you represent it? In the decider notation. 6 uses what? Decider notation. IP version 6 uses decider notation. Explain this one to me. Where did this come from? Getting this. You are not getting this. In the decider notation, what is it? Blocks. What is the first address of the block represent? What is it the block represent? Nothing. What is the, do you remember the decider notation? Blocks. Yes? What is the first address in the block? The first address in the block? Network. Clear? The address of the network, the prefix. What is it? All of this, by the way, in the final exam, I was saying. So you better review it. What is this? 1000. Why it is 2000? Why it is 2000? For the global unicast. Because the always what? Is 2, like I showed you a moment ago, which is 2. Yes? Yes? Prefix. 00 what? 1. 3 bits. 001. So it's what? /3. That's a prefix. Yes? And what are these? It means all of them are what? Zeros. Is this the address? Can we use this address of the block? This is the address of the block. Why? Because all the hosts are what? Are all what? Are all zeros. Are you following me or not? This is the, so for example, what is here? Can you give me what is the first host here? In this block, which we refer to unicast, what will it be? It will be 2000, yes? And then what? All what? Zeros, except for the what? The last bit, which is a 1. Did you get this or not? Did you get this or not? So on and so forth. So we call it what? We call it /. Now, there are some special addresses. If you see the prefix is what? All zeros. Prefix is what? 8. 8 means 8 zeros. Yes? Which means how many hexadecimal digits? These are what? 2 hex. 2 hex. Each one represent what? Each 4 zeros represent a what? Yes? So 00/8. The remaining are all zeros. These are what? Special addresses. One of them, the all zeros. One of them is this. Let's see if you can help me. You see this? Look at this. What does this notation mean? 0, 0, double colon, /128. What does it mean? All of them are what? Now, is this a special address? This is a special address. Why? Because it starts with a what? It starts with a prefix, which is what? 8 zeros. That's zeros. Yes? What is this for? What was the old 0 for in IP version 4? And what was the all zeros used for? And what was the all zeros used for? The all zeros was used for as an address when a host, what? When a host it tried to get a what? Tried to get an IP address from a DH server. Clear? Okay, then you what? To configure to get an IP address from a DHCP, at the beginning, when you boot up your computer, you need a special IP address, which is what? Which is the all zeros. In this case here, it's the same thing, all zeros, 128. Did we see a loop back? What was the purpose of the loop back? What was back in the case of IP version 4? In the case of IP version 4, the loop back was what? Remember, the address is what? 127 dot what? Dot 0.0.0. This is the block. First in the loop back is what? 127.0.0. Dot what? 1. In here, what is this one? Can you read it for me? What is this? 0, 0. The first 8 zeros are what? Zeros. Yes? The remaining are all what? Zeros. Last one is a what? 1. What happened to the leading zeros? The leading zeros were eliminated. Along way or not? Were eliminated. So you get what? 1 and slash what? 128. Again, slash 128. This is used for what? It's used for loopback. Now, let's look at, which is very interesting. And that's what? Compatible, IP version 4 compatible, IP version compatible, and IP version 4 mapped. Let's see if you IP version 4 compatible first. Compatible means what? That a host is compatible with both what? IP version 4 and what IP version. They take the IP version 4 and they put it here. In the what? In the first how many bits? 32 bits. Clear? 32 bits. And the remaining are all what? Zeros. How do you represent those? How do you represent those? 0, 0, 0. Yes? And then what? 2 colons slash what? 96. Why is it slash 96? Slash 96 means what? The prefix is how many bits? 96 bits long. Yes? Host address. The host address or the interface address is what? The remaining 32. So this is what they do. The IP version 4 mapped. This one is what? Compatible. You just copy version 4 mapped. You take the IP version 4 address here, which is 32 bits. And what? All ones, 16 bits of all ones. And then what? 80 bits are what? Are all zeros. So you get what? You get this. What is this? 0, 0, 0, 0, double colons. And then FF. The FFFF is this, the all ones. And then slash what? 96. Clear? Clear? Okay, so different, there are different what? Different addresses. For example, in a multicast, this is a multicast. In a multicast, it's what? It's F0. What is F000 means? And then double slash what? 8, slash 8. What does it mean? At the beginning, what do you have? You do have, how many ones are there? 8 ones. Are you following me or not? Okay, and then slash what? Slash 8. Then you do have different types of multicasting. So, for example, there is a flag here that tells you whether it's multicast or a what? Transient multicast. Permanent multicast means what? It means that you are going to have multicast address to use for all of your multicast. Transient means what? Temporarily. You use an address, and this is a group ID. A group ID is what we refer to in IP version 4 as what? Group address. In a group multicast address in IP version 4, there were what? There were 28 bits. Here there are what? 100 bits. A large number of what? A large number of multicast groups. One? No, this is a typo. It should be what? I'm sorry. FF. Why is it FF? Because how many? We have 8 ones. So every F is what? Is 8 ones. The other one, the other F is what? Is 800 slash 8. Do you understand the slash notation? Everybody understood the slash notation. Also, it has 2 different addresses. All of these are referred to as what? All of these are the special addresses in here. The special addresses are global unicast. IP version 6 also 2 types of what? Addressing. It's called unique local unicast and link local unicast. Unicast or link local address. In addition to the what? In addition to the multicast address. Listen, what is the purpose of this? The purpose of this is the following. What is self-configuration means? In IP version 4, when you want to get an IP address, you need to contact a what? A DHCP, or representing the DHCP. Clear, the DHCP relay. Are you following me or not? Yes? But we need to and then, by the way, how would you map an IP address to a MAC, an IP version 4, How do you map an IP address to a MAC address? You map MAC address through the services of who? Through the services of ARP. Clear? The question that the IP version 6 people faced was the following. An IP version, the size of the IP address, 32-bit long. What is the size of the MAC address? 48. They said what? They say the 48 does not fit inside a 32-bit. Did you get my point or not? They tried to find a situation in which can configure itself without the need of the help of who? P. Did you get my point or not? Did you get my point or not? Can a host configure itself? They call it what? Auto configuration. Without the need of what? Need of a DHCP server. Clear? Okay. A host has a MAC address. The MAC address is the address of the what? Of the NIC card. How many bits long? 48 bits long. Now, in IP version 6, how much was the interface identifier? The interface identifier, this one here, how much was 64, which means what? It is more than 48. Whereas in how much was this? It was less than 48. The whole thing was 32. In IP version 6, just this one is 64. So what did they do? They allow the host to MAC address, his MAC address, which is what? 48-bit long, and put it as part of the what? As part of the what? Interface ID. Yes? How many do we have here? We have 6, which means what? The 48 bits, can it fit here? Can it fit here? In here. Now what did they do is what? They took the first 24, they put it here, the last 20 put it here, and in between, they separate them by what? All ones. Are you following? Yes? And then what? And then the remaining are what? All zeros. Except one is what? FE80. Do you understand where is FE80 came from? F is what? 1111. E is what? 1110. Yes? What is this? 1000, which represent the what? Did you get this or not? Okay, and slash what? Slash 10, which means the first, slash 10 means what? The first 10 bits. Clear? And this becomes your what? Address. This IP address can only be used what? Locally, with that a link local. It can only be used what? Locally, on the link. If you want to use a global unicast, which is what? Which means that when you go outside the site, then you need to get a global unicast. This one is only if you want to use it what? Internally. You can go by yourself. You don't need a what? A DHCP server to assign an IP address for you. Clear? You can use what? You can use your what? You can use your MAC address as part of what? As far as the copy it in here. Clear? Clear? Okay. So different types of addresses that were introduced in IP version 6 to make it a little bit more what? More appealing. The future of IP version 6 is still what? It's still up in the air. A lot. You check, by the way, if you check your interface card, if you check your adapter card in your computer, what does it mean when I say if you check your adapter card in your computer? What does it mean? It means you go to the what? IP configuration / what? All. IP version 6. Try it. You will see IP version 6 adapters in there. Are you following? You will see IP in there. So most of the new operating systems support IP version 6 already. The is what? Is that can we deploy this on a what? On a an internet-wide. And remember, once you finish from the transition period going from 4 to an IP version 6, you will need to eliminate IP version 4 altogether. Eliminate IP version and stick with what? Stick with the IP version 6. This transition period cannot continue for clear.
Professor?
No response. Did you get it? Okay, good.
Professor?
Yeah, I think we spend a lot of time on this, but you needed to know these things because a lot of products currently are compatible with IP version 6. So we needed to know a little bit about it.
5 minutes.
Thank you very much. Now, next we will move to a new subject, and will take us into the real broadband technologies other than just what or DSL or so on and so forth. And this is the use of what? This is the use of optical. Now we divided this, I posted the charts already, into two bases, into two sets. We are going to be looking at what? Two types. The first one, which we refer to as a SONET, and the second one, we refer to it as what? The wavelength multiplexing. Dense. This is called what? Dense wavelength division multiplexing. And this one stands for what? Synchronous networks. Now this one, of course, this one came before this one. This one supports this one. This one supports this one. And SONET runs over what? Over DWDM. In other words, if you think about the layered architecture, about the DWDM as the what? As a physical layer, and the SONET runs over what? Layer. Runs over that layer. Now the SONET by itself, it has a what? A physical layer and a what? A link, a data link layer. But when you support SONET over DWDM, DW ultimate what? The ultimate physical layer. The SONET will reside on top of it. But we need to understand the SONET. We go into the DWDM. SONET stands for what? The synchronous optical network. Now, why do we need this? This is an standard for interfaces. At that time, there were no standards for optical interface. When I say no standards, a company with a given optical interface, they talk with a what? A product from another company, which also has what? Clear? They needed what? They needed a standard to allow equipment or devices from multiple companies to communicate with each other. So they developed what is known as the SONET. It was developed by, called what? Bellcore. Bellcore was, before it belonged to what? To AT&T. Why do we call it optical? Everything, all the transmission is optical. You mean why they call it optical? Oh, he is asking you? Oh, and instead of why he is not asking me? Okay, optical means what? Means everything is what? Everything is optical, the switching is optical, the interfaces which are what? Or the transmission fiber, everything is optical. Clear? That's the current network. The current network in the all based on what? Based on the optical technologies. The SONET and the what? The DWDM. Currently, all of these networks, all of these routers, for example, interconnected. Do you think they are interconnected by? They are all interconnected by what? By optical interface. Optical interfaces, what? Optical fibers and so on. So, clear? Clear? They decided that they are going to develop an optical transmission interface, and they call it a SONET. Bellcore, again, as I told you, was a company. They used to call it what? Bell Labs, and it used to be. Right now, I mean, not right now, I mean, some time ago, they themselves from AT&T, so it's separate things. Okay, it established a standard multiplexing based on what? 51.84 megabits per second. They call it what? OC1 stands for what? Optical carrier level what? Now, in the digital hierarchy, the one that we studied in 450, everything was based on what per second? Remember the 64 kilobits per second. So we have what? DS0, digital signal 0, 64 kilobits per second. One, which we refer to as what? A T1, consists of how many voice circuits? Support 24, 64K, for a total of 1.544 megabits per second. DS2, 6.312 megabits. DS3 is 44.736 megabits per second. Clear? That's the digital hierarchy. It's the SONET or the optical hierarchy started building based on what? Based on 51.8 bits per second, which they refer to it as what? As an OC1.
We're out of time.
But we ran out of time. And next time we will continue on this. Thank you. Clear? Okay, good.
This concludes E555 with its April 8th, 2014.